Welcome. Let me just say something more about the problem of extending the Lefschetz fixed point theorem to polynomial maps. And when you look at this problem, we cannot use simplicial maps. So here for simplicial maps we have a nice Lefschetz fixed point theorem. We have also a very simple proof. We have just McKean-Singer symmetry, which tells us that we have here for the Koopman operators, the supertrace of the Koopman operator is the sum of the indices of the fixed points, and here we have the supertrace on cohomology. So we want to extend this, and this week I thought maybe it's a good idea to look at open sets, dynamics of open sets, rather than look at correspondences. I don't like so much correspondences. And so if you have a nice topology here, finite topology on a simplicial complex, and so we can look at a map on topology by just defining it on vertices, like we did here for the simplicial. Simplicial maps are more special than continuous maps. They come from maps on vertices. So that's also what we want to have here, that we kind of take the atoms of the vertices and we just describe it there, and then once we have the map defined on vertex atoms, we have it also in general. So the pointless topology works pretty well. I was distracted a little bit by thinking yesterday about connection calculus. There is a nice connection calculus which is kind of not so much compatible with the Dirac calculus. So there's fermionic and bosonic thing which we have looked at. And if you look at the connection matrix, this is a very nice matrix because it's unimodular. And also the inverse, this green function matrix, is unimodular and has finite range. It's very nice that there's this symmetry here. And I thought maybe just to define a dynamical version of this. So this would be for the identity, and you take for the transformation T, you take just this definition, which ties into the topology, because what you have here for the green functions, you have the open sets which matter. Right? This is this green star identity. I call this green star identity, that this is the inverse of that. And it turns out this is not always the inverse, so I have still to kind of find the right definition. So this needs a lot of experimentation. So with this definition, it's not always true, but what is experimentally, I see that this matrix is always unimodular. It's very exciting because it's not obvious, because these matrices are not symmetric, and so still we have this unimodularity. So I don't know yet what is going on, but I was thought, oh, maybe this GT would be a good Koopman operator, kind of an analog of the Koopman operator, because we have in the diagonal something which looks like indices of fixed points, fixed open sets, and but the whole thing, it's not compatible with the dynamics of the Dirac part. So I tried other things like so I have still to experiment here to see what works. But I wanted to get back to the example which I showed last time, and in this example, this is very important to know what happens when you have the map x goes to nx, or x goes to kx on a discrete circle. Because if you understand this, you understand the map z to the n on the Riemann sphere, because locally it is just given like that. So here the indices are -1, should be -1, there should be one index -1. That's you see classically, or if you have a map kx, you should have k -1 fixed points of index -1. And that's what you also then expect in the two-dimensional, in the complex case, where then the indices become positive, just because of the dimension is one larger. So we have then positive indices, and so the map z to the n would then produce index n -1. So that would be kind of just, that's what we want, right? Because we look at fixed points and not at roots. And so we have then, we want to have the same story then in the continuum Let me just show here how this definition works here. So we just say what happens for an atom of a vertex. Like here, the yellow thing is the atom of the vertex 0, so that kind of gets expanded into an open set, and then we can then look what happens when we take the intersection, right? When we take the intersection, what happens to an edge here? So that would be then just the intersection of this with this. The point 0 and its adjacent edges are fixed. They are mapped into themselves, and so the edges have index -1, they have value -1, and the point itself has value 1. So this is the index should be -1. And in another case, in all the other case here, there is just no fixed point, because this edge goes here, right? This point 1 goes to 2, so there's no fixed point. I still have to think about this, and also then the related thing, if you take maybe c squared plus c, you know, if you take a map, which is more interesting, right? If you take c squared plus c on Zn, that's a very important map in number theory, because it's used in polar row for factorization of integers. In the integer factorization, we look at these maps, and they behave like random maps on Cn if n is a composite number. So it's kind of an interesting also link to number theory, what happens here. But we would really like to have a Lefschetz fixed point theorem in a situation which includes also expansive maps, like the multiplication by a constant or polynomial maps in the discrete complex plane. So this is a work in progress. I still don't know where this is going. But that's it for today.